And now we will have a talk, the last talk of this workshop by Pertti Hakonen, which is going to be about voltage-voltage correlations in gate-controlled superconducting nanowires. So, Pertti, if you're ready, go ahead.
Thank you. And thank you all for staying to the last talk. And I also want to thank Anton and Florian on organizing this excellent workshop. I've enjoyed it a lot. This talk, I think I start a bit telling what Nano Group is doing at the Low Temperature Lab here at the Applied Physics Department. So here you can see the lab in wintertime, lots of snow sometimes. So our work deals with several topics. So for example, we are working on quantum amplifiers and entanglement. So we have been working on various Josephson junction-based parametric amplifiers, characterized entanglement. At the moment, we are very much interested in multi-partite entanglement in these systems. And also for quantum circuits, we are at the moment very much interested in silicides, superconducting silicides. So we think they are very nice platforms for quantum circuits. We are interested in correlations in quantum circuits. So we have done lots of work on Cooper pair splitting, trying to preserve the entanglement of the spins. Also, we are interested in solving the problem of 1OF noise. That's a very old problem. And we are also interested in gap topology. So you will see some results on that. We have worked a lot on hybrid circuits, surveillance circuits. So carbon nanotubes, graphene. We have done microwave sensing using graphene junctions. We have used carbon nanotubes as templates for atoms and done Bose-Einstein condensation type of experiments in these systems. And the nanowire dynamics, which is listed here last, this is the topic that I'm going to talk most today. We have done lots of graphene and 2D material devices for sensing. And for example, graphene is very clean. If you have suspending graphene, it's very clean. You can introduce impurities and study the impurity motion and verify theories on the basis of this. So let me start with this one. I like this because this is basically thermally pumped quantum device. So it's a device. Let's see how this works. Maybe it's better I take. Okay. So this is a graphene device which is on a superconducting cavity, so microwave cavity. But in this case, this graphene device works as a very nonlinear resistor. And when you pump this cavity, so it's a regular LC circuit with this very nonlinear resistor in parallel, when you pump it, you get a thermal instability. And here is the voltage across the device as a function of time. So this is microseconds, so there's very rapid change. So it behaves like having two different regimes, one with high Q and one with low Q. And this comes from a thermal instability. And you can see the emission from the system shown here. The spacing here between the different peaks, it's the thermal oscillation frequency in the system. And in fact, now, if you select one of these side peaks here, you can make this as a parametric amplifier, and you can get pretty nice operation. So the noise temperature is 1.4 Kelvin, and the gain is decent. So it's a very nice demonstration coming from the fact that graphene can respond very quickly. So you can vary the temperature at 10 gigahertz, even you are at low temperatures. silicides, these are our favorites at the moment. We have done microwave cavities using silicides, and we have studied the kinetic inductance in these systems. That's basically related to the resistance in the normal state divided by the gap. So if you have a very resistive device, then, or very thin device, narrow device, then you have large resistance and have large kinetic inductance. And we have studied that. It's shown here as function of temperature. If you now plot the deviation from the zero temperature value, you get this inset. So logarithmic scale for the change of the frequency as a function of temperature. And you can see that it's a Power law behavior, and this Power law, there's an indication that it's not the regular BSS type of superconductor, but rather it has also triplet pairing. And this Power law is an indication of that. This is collaboration with Venkat Chandrasekhar in the US at Northwestern University. So this is a system where we are studying the gap topology in this kind of multi-terminal normal system. So we have superconducting loops by which one can apply phase bias on this multi-terminal device, and you can map the gap structure as a function of these bias phases here, phi 1, phi 2, and here you have the topological numbers for the different states that you have in the system. And now here, if you go from here to here, then you go across zero gap, so you change the topological numbers. In the experiment, it's not exactly equally visible. This is what we measure, but still the resemblance of this plot with these plots here is pretty good. This is something that we are going to continue. At the moment, we are making a device using graphene, and we are going to have even more than 2 loops for phase biasing. Now, the carbon nanotubes, they are chiral systems. And then if you try to put helium-3 atoms on it, it's difficult to match the natural structure of helium-3 on graphite on the nanotube. So you will have frustration for the helium-3 structure. And since you have curvature in this system, then you can have dimers. And now, due to the frustration, you will have vacancies in the structure. And these vacancies, they can delocalize at the lowest temperatures. So you can reach a supersolid state in a system where you impose vacancies by the structure. I mean, of course, you would like to have a system where you have 0-point vacancies, but that has been tried several times with helium, but it has never worked. But here, having this carbon nanotube template, you can do it, and you can get the Bose-Einstein condensation in this system. Here you can see the transition temperature as a function of the size of your sample. So you can vary the size of this sample by varying the coverage of your system. So when you vary the coverage, you basically have higher density at the edges and then low density in the middle. So you can vary the length of your dimer phase, and you can then vary the transition temperature. So this fits the 1D expectation values. So I mentioned already that graphene is very clean, so you can put impurities. In this case, we have put neon atoms on graphene, and the atoms, they will diffuse on the system. So here's a Monte Carlo simulation. You can see it tends to make some clusters and then decluster. And using this kind of model, you can then analyze the results that we have obtained on 1F noise in this system. And everything fits pretty nicely for this kind of clustering, declustering modeling in the system. So you will get anisotropic mobility fluctuation in your system. And in this case, when you have this kind of anisotropic mobility fluctuations, then there's a special point. If your mobility times magnetic field is 1, the noise will vanish. Of course, in practice, in our case, it doesn't fully vanish. In our case, the correlation between the different directions of the mobility fluctuation is not perfect. And in this case, you don't really get this full suppression of the noise. We have also studied the noise of the noise. So here, these are traces of the noise spectra. So each point here is one noise spectrum. And we then look how the noise varies with time. So this is a so-called second spectrum. So it's a noise of the noise. And if, I mean, typically people say that when you have 1F noise, it's a collection of fluctuators. But if you have a collection of fluctuators, then the second spectrum would be flat. So it would be white. But here, in this case, when you have this true 1F noise, so you have long time correlations because of this clustering, declustering, then you have second spectrum, which according to theory should be 1, but in our case, it's close to 1. So it's almost like 1F noise. We are very much interested in graphene, quantum Hall stuff. So the ultimate goal is to get some non-abelian particles. One very famous fraction is 5/2 that people have studied for a long time. We have done some experiments on that in graphene. So we have had a quantum point contact, and we have worked on this 5/2 state, but we have realized that it's not that easy. So typically you have some equilibration in your system, and instead of having just simple 5/2 states, you have fractional quantum numbers, which are combinations of the different regions that you have in the sample. So this is something that we are continuing, and of course we want to put superconductivity in that as well. Now this is describing some collaboration with Dima Efetov at LMU. So we have collaboration with him. This is a sample that Dima's group has done for us. These are twisted magic angle bilayer graphene, or supposed to be magic angle bilayer graphene devices. Here you can see that they are close to the magic angle. Unfortunately, when we have measured these, the resistance doesn't go all the way to 0. So here is current, and here is the resistance. You can see that it's about 1.5 kilo ohms. And this is very unfortunate because this experiment was supposed to measure the kinetic inductance of these devices, so superfluid stiffness of these devices. But since it has this resistance, you can't really measure the kinetic inductance of these devices. So here in this plot you can see the superconducting regimes. So one is here, and the other one is then here, and then the third one is on that side here. But instead, one could measure the electron-phonon coupling, so you can put heat into your system and look how your temperature changes, and the prediction is that the magic angle bilayer graphene has much stronger electron-phonon coupling, and that basically comes from this change in the Fermi velocity. So when you get flat bands, your Fermi velocity becomes smaller, and then your electron-phonon coupling becomes stronger. So this is something that we are finishing at the moment, but I will not tell more about that. Okay, but now up to the main topic. So this is related with the gate-controlled superconductivity. So this is a very interesting topic, and in fact this is behind our cobalt silicide or silicide work altogether. So we want to make gate-controlled superconducting devices. you can see the structure that we are interested in here. So there is a nanowire with gates, and then one looks how the supercurrent here is changed by the gates on both sides. So here is a brief outline. I will tell a bit about background of the gate-controlled superconductivity and noise, and the models people use for describing this, and then I will go to the experimental details and results and discuss both switching noise in the system and shot noise in the system. Here you can see the background on this kind of gate-controlled superconductivity. This is a device from Francesco Giazzotto, measured some like 7-8 years ago, and this is the data. So here is current, and then gate voltage is here, and you can see the supercurrent going down with increased gate voltage. So you have a state where your system is switched off, and then a state where your supercurrent is on. But it's not fully clear what is the reason behind this phenomenon. And we have done noise experiments both at low frequencies and at high frequencies. So at low frequencies we get switching noise, and at high frequencies we are aiming at shot noise of flux pulses, phase slip noise. Just quickly, the switching noise, so if you have a system with two states and they are characterized with two different responses, this can be change in the voltage, as in our case, or it can be a change in the resistance. Then in this kind of time trace, if you do the Fourier transform, you get the regular Lorentzian spectrum. So there's the basic fluctuation spectrum, and tau is the mean of the one period time. And then if you have lots of this kind of fluctuators, you sum up, let's say, if you have a uniform distribution of the energy barriers, and you sum up all the spectra, you get the 1F noise spectrum. The phase slips, so the complex order parameter is shown here, and this plot shows the variation of the real part and imaginary part of the order parameter as a function of position on the wire. And you can see this is the regular uniform superflow region, but here you then have a suppression of the order parameter amplitude, and at this point you can then have your phase slip, and you have a voltage pulse at that point. So you can have either quantum fluctuations driving this, or you can have thermal fluctuation driving this, and many people, they're very interested in the quantum regime with coherent phase slips, and people have even used these for making quantum phase slip qubits. And now, just to give a background of why we think that we can have bunching of these phase slips. Here are a few formulas. So there is a phase slip rate, which depends strongly on the critical current, which depends on temperature. And now, when you have phase slip, you will have heating in your system. And then the question is, what is the heat capacity of your system? How much the temperature will increase by one phase slip? And if it increase a lot, then of course this rate increase a lot, and you will have then additional phase slips following. Or it's of course possible if you have a very large change in the if the heat that you put in compared with the heat capacity is very large, then of course single phase slip is enough to just drive the system into normal state completely, and then you will not have any bunching. But if you are at higher temperatures, then the heat capacity is bigger, and then you can have regions where you don't make transition with one phase slip, but you can have a increased rate, and you have a bunch of phase slips. And this is what we would like to measure here. And how do we measure that? So you know the shot noise. So you have charge, integral of current, and basic unit is E. So here is your shot noise, 2EI, and you can write it in terms of frequency, E squared F. And now for the phase slip noise, you just change the charge to flux quantum, and then you use the same equation now with flux quantum, and you get that your voltage noise in the case of phase slips, it's 2 times phi 0 times voltage. And then this ratio, if you measure your noise and divide it with the Poissonian noise given by this formula here, then you get Fano factor for the voltage noise. And this Fano factor, this would be a measure of the number of quanta that you have in one phase slip. The regular model for studying these things, it's so-called tilted washboard potential, which is illustrated here. I mean, you can write down the current through a Josephson junction, the supercurrent, displacement current, resistive current, and then you get this kind of equation of motion for your system. Here I is the bias current through your system, and this basically equivalent to motion of a phase particle in a washboard potential which is tilted by the bias current. And the important things here is the plasma frequency, which is basically the motion of the phase particle in the potential minimum, and how big is the dissipation. So they give you the quality factor. So if your quality factor is high, then your system can fluctuate easily, and it can easily start running along the potential. And here are graphically the situation. So you have the potential on the top, and then here is the phase behavior, and this is the voltage. So if you have very small tilting of the potential, you can have very infrequent phase slips and very infrequent voltage pulses, and this is the case where you have the shot noise in your system. If you have rather big bias current, then you will have bistable behavior. So your system may run for some time and then stop. So you have like a phase which is running for some time, stopping, running, stopping, and your voltage is given by this trace here. And if you run even faster, if you drive the system even stronger, then you will just continue to run and you are in the normal state in the system. So the expectation is that if you look at the frequency-dependent noise, so here if you take the log of your noise, plot it as function of log frequency, then you have the switching noise at low frequencies, and then at high frequencies you have the shot noise. In Josephson junctions, people have done calculations, and it's illustrated here, and these graphs, they illustrate the importance of the quality factor. So if your quality factor is large, then you can have huge noise at high currents. If your quality factor is small, then the system is stabilized and you have single phase slips. Of course, this is not exactly the calculation for our case, but the theorists are saying that qualitatively this should be fine. And at small currents, you can do analytical calculations, and you get the high volt cotangent behavior, which is basically this initial decrease here. Okay, experimental results. So the device is like this, and we measure both the current through and the noise of the current through and the noise of the current from the gate. Here you can see the results on the switching current as a function of gate voltage, and you can see that when you go above 3 volts on the gate, the switching current starts going down. Also, you can see that the IV curves are getting different. You have some structure before the switching current. This is the leakage current, how it goes as a function of gate voltage. And now here you then have the noise of the gate leakage current. It's shown here. Or you can take a look on this one. So you can see that when you have leakage current, your noise goes up. And it's clearly like 1 noise in this. And you can do at the same time the measurement of the current through the device. So this is now the noise of the device, noise of the current through the device, and the colors refer to these points here on the plot on the left. You can see that when you are at this regime where you have the switching going on, you get the biggest noise. And you can also do this in the time domain. So here are now traces in the time domain. There is both the noise of the device and the noise of the leakage current, and you can see that there is a strong correlation between these two. And you can calculate the coherence, and the coherence is given here. So you can see that the coherence is pretty close to 1. Coherence is defined here. So it's basically cross-correlation squared divided by the individual autocorrelation functions. You can also study in more detail the behavior of the system. So you can analyze the switching rates up and down. You can make distributions of the values of the lower level and upper level, and you can make distributions of the time the system spends in the upper or lower level. So you can clearly see from these distributions that it's Poissonian switching between the two levels. So this upper data is at the sharp edge of the IV curve. If you now go lower to lower currents, then the behavior is a bit different. You have like switching up and down from an intermediate level, and you can then make distributions, and you see that you have like 2 different peaks here at lower voltages, and then if you increase the current, you get this peak at higher voltages. So you can deduce from here that in this case, you have like small region becoming normal in the system, and here, in this case, you can deduce that the whole wire becomes normal. Taking also into account that if one compares the results from first cool down and second cool down, there's a huge change in the critical voltage range. So the interpretation is that in these systems, the leakage current is going through intermediate trap states in the barrier. So in our case, it's the substrate, which is silicon dioxide, where you have this. And this is, in fact, a result that is known already with CMOS devices and various FET structures. Okay, so shot noise results.
1 minute?
1 minute, okay. Very good. So that's, you need high frequency amplifiers, circulators, bias-Ts, and you need to do a careful calibration. You have to account for all the noise sources of your system. And here is then what you get. We are measuring both the total noise and the integrated differential noise. The right one is the differential noise integrated, less noise, but basically the same results. And from here you can see that if you look at this, then you have just single phase slips here and it becomes normal. But in this range here at 400 millikelvin, you can see the region where you can have this bunch shot noise phenomena. And this is what we see. We get like 20 in that range, 20 phase slips in one bunch, and at low currents it's like 1, 2, or 3 in this case. And so we are still working on the analysis, and I think we should really think about trying to improve on the tilted washboard potential. Okay, maybe I don't talk about that. These are the people who have been working in my group. Then there are people at NYCU in Taiwan. These people are helping us with silicides, Shengshan Ye and Junjong Ling. And then in nanowire business, we have been collaborating with Peter Mak and Chabal Chonka and Jesper Nygård in Niels Bohr Institute, and at LMU with Andres and Dmitry Efetov. Thank you very much.
Thank you very much, Pertti, for your talk. Now this paper is open for questions. Any questions? Yeah, JP.
Very quick, yeah. Something very quick for the nanowire. So why not just put the boron nitride, then you put the contact just under the nanowire, rather than put the contact far away for the gate?
Leakage current through boron nitride. I mean, that's tunneling current. Of course, one could try it.
Okay. I have a question also, for example, in the case of liquid helium on the carbon nanotube. How do you manage to get the helium to stick to the, or to be around the carbon nanotube? Do you dip it in the liquid nitrogen, in the liquid helium, or? I
mean, you just fill the cell with some helium-3, and then you let it relax for 1 day, and that's it. I mean, the absorption potential is pretty strong of helium on carbon nanotube.
Excellent. Thank you. Any other questions? If not, then let's thank the speaker again.